Hi, in this video I will show you how to get the Newtonian limit using the Langevin equations for quantum mechanics. Let us see. The problem of the Newtonian limit is an ancient problem in quantum mechanics. Sometimes we have approaches that use the h bar going to zero as a condition for the Newtonian limit, sometimes called classical limit. But this, of course, cannot be done directly in the Schrödinger equation. It makes no sense, of course, to have something like Vx c equal to I h bar 0. Of course, this makes no sense. It also makes no sense to make the h equal to 0 directly in the psi function, the probability amplitude. So sometimes it seems appropriate to use this condition, this limit, in the results of some concrete experiments that we are studying. But the fact is that this kind of approach to Newtonian limit is not very systematic. Another possibility is to look at the Bohmian formulation of quantum mechanics and look at the quantum potential, which is presented here, and assume that again h bar goes to 0. This will apparently gives the quantum potential equal to 0, and then we will have just the Newtonian equation. But this is wrong. This is wrong because this function here, which is part of the solution of the Schrödinger equation, can have inside it h bar. So you cannot do that. Now we can see how to tackle this problem within the limits of our own interpretation. And we may use the Langevin equation to make that. So look at the Langevin equation again. And we have here, besides the Newtonian force, two terms, this one and this one. This one related to fluctuations and this one related to dissipation. And we note that in both terms we have the appearance of the parameter gamma. So of course it is easy to see that if we make gamma goes to 0, we may get rid of the fluctuation and dissipation terms. But these terms are exactly those that are related to the fluctuation dissipation theorem. Thus we may conclude that Newtonian mechanics is just quantum mechanics without the fluctuations and dissipations. And this is natural to think, at least within the realm of this interpretation, because we are portraying quantum mechanics as just a stochastic theory, which includes in the Newtonian theory just these two terms here. This one, which is related to fluctuations, and this one which is related to dissipation. Now we will show you by means of some simulations how we can pass continuously from Newtonian mechanics to quantum mechanics by just changing the value of this parameter gamma. Let's see how this can be done. We now have again our simulator, and we would like to make gamma equal to 0. It's here. I just have to click here and the Newtonian system appears with all the parameters that are necessary to make the Newtonian simulation. And look what happens here in this panel and also in this panel here. What happens if I just make the simulation? We have here the point making its trajectory in a circular path because our Hamiltonian is just the Hamiltonian on phase space of a circle. In this pen here, I have just the representation of the usual probability density function for a harmonic oscillator. It passes much of its time at the border of the potential and less time in the middle. Okay, now we can change for continuously this value of gamma. Let's put 0.05 for instance and make the simulation again. Let's see what happens. Note that now the trajectory is a little bit different from the classical Newtonian one, but still is a trajectory that we can follow. The probability density function changes a little bit too, and we are just getting out of the Newtonian limit. Let's change the gamma factor again, now with a value a little bit greater, and let's see what happens. Note that the fluctuations are stronger. They depart from the classical Newtonian pattern very much and become to be quite random. The probability density function changes a lot. We can now put a much higher value. Let's put 1 for instance and make again the simulation. Again, the fluctuations depart very much from the Newtonian case and begin to fill the whole phase space. Finally, let's pass to the default values and try to make the simulation again. If we do that, we get exactly what we was getting before, which gives the true probability density function both on phase space and on configuration space, as we will see when I plot the function, the theoretical function obtained directly from the Schrödinger equation. So let's wait a little bit and let us plot the function and look at the results. The results are very precise. This, of course, can be applied to the excited states because since we are making the fluctuation dissipation terms equal to 0, it doesn't matter in which state we are. We can also make the same simulation for the Morse oscillator. I will do that in another video. Okay, this is what I would like to show you in this video. In the next video, I will show the same results for the Morse oscillator. I will show you that another physical system different from the harmonic oscillator gives the same result. It's important to make this kind of different simulation because we know that the harmonic oscillator is a very special case of quantum mechanics. It's not interesting to base results, mainly interpretational results, only on the behavior of the harmonic oscillator. Well, this is what I would like to show you now. Thanks for watching.